All right, hello everybody. Welcome back to data analysis. So we're going to pick up this lecture. So this is going to be a second part of a lecture which began on confidence and prediction intervals, and we're going to pick up with alternative measures of model fit. Okay, so I say alternative measures of model fit, and this is well, the alternative here is to root mean squared error, which is our model of fit which we've used throughout the course, and we're going to do some alternatives to root mean squared error and talk about pros and cons compared to root mean squared error. So the first alternative measure model fit that I'm going to introduce here is mean absolute deviation. So like mean squared error, mean absolute deviation does a pretty good job of the vocabulary does a pretty good job of describing what's in the equation. So mean absolute deviation of an estimator y hat compared to the truth y is mean absolute deviation. So we have absolute value of their difference here. Okay, and so this contrasts to the mean squared error, where we have yi minus y hat I, right, squared. Okay, so mean absolute deviation has the advantage that its units are the units of y instead of the mean squared error being in the units of y squared, and that justifies taking the root of the mean squared errors to make sure we have the units in y. It's more interpretable. So that's one alternative measure of model fit. You can also call mean absolute deviation mean absolute error. It means the same thing, just two words to describe the same quantity. The other alternative measure of model fit we're introduced is r squared. So r squared is 1 minus, and here we have what looks like a mean squared error in between y and y hat, except for we're missing the 1 over n out front. And in the bottom we have the sample variance, what looks like, the sample variance of y, y minus its sample mean, but we're missing the 1 over n minus 1 out front, right? So you can imagine, right, we could, if we wanted to, for interpretation's sake, multiply both of these by 1 over n, or 1 over n minus 1 if we wanted to. Whatever we do to the top, we can do to the bottom. But we can interpret this as so this is the sample variance, right? And this is a ratio of the sample variance, okay? And so this explanation, so you can just think this through with these expressions, but this r squared is sometimes described as the proportion of variance explained, okay? So r squared, it's a fact that r squared will be between 1 and 0. This is sort of similar to correlation in the fact that it's unitless, and so this number cannot be bigger than 1. If it's 1, we just are predicting a constant sample mean here. If this inner quantity is 1, making the r squared 0. Likewise, this thing is positive, so r squared is bounded above by 1. Okay, I don't actually like this explanation, proportion of variance explained. It's an old school way to describe r squared. The reason I don't like it is because of this word explained, right? So when we say proportion of variance explained, it's like for me, this language implies causality, in the sense that we are talking about where it comes from. We're explaining the variance, but not really. We just happen to have some predictors which when we take this ratio makes r squared larger or smaller, right? So yeah, we'll talk about some more pros and cons of r squared, but r squared has been used more heavily in the past. I think it's a little more old school in terms of measuring model fit. If people who are trained some years ago will tend to rely on r squared, whereas more up-to-date way of measuring model fit is with root mean squared error. And like I said, I'll talk about one big drawback of r squared here in a little bit. Caret will give both of these measures of model fit by default. So usually what will happen if you fit a model in caret, it will select, for example, in principal component regression, it will select the number of components to keep, using our root mean squared error as its criterion, but then it will print mean absolute deviation and r squared by default. So these are what these numbers that are being printed. So if you call summary on an LM object, okay, it will print the two things. R will print the what it calls the multiple r squared. Okay, multiple r squared is what I've described over here, and it will also print what it calls the adjusted r squared. So multiple r squared is this. Adjusted r squared, what you do is you do 1 over n minus 1 in the denominator and 1 over n minus p minus 1 in the numerator. So here we're accounting for the number of parameters being estimated here. So this constants in the numerator and the denominator don't cancel in adjusted r squared, but they're very similar in their interpretation. I think it's a little bit splitting hairs to talk about why you would prefer one over the other. But I guess, yeah, so from a theoretical perspective, both of these are unbiased estimators for their respective variance terms. Okay. So why would we use these measures of model fit over something like root mean squared error? First, let's consider mean absolute deviation. A big benefit of using mean absolute deviation is that it is more robust to large measurements. Okay, what that means is that if you have, for example, a value a residual which is extremely large, you take more of a penalty in the mean squared error than you do in the mean absolute error, and that's because x squared will be larger than absolute value of x. Right? So for x large in absolute value, this x squared will dominate, and so what happens is large values will have a less dramatic of an impact on your estimator, and that will lead you to be less sensitive to extreme measurements. This is similar to the relationship between the mean and the median. The mean is more sensitive to large measurements than the median, and this parallels the mean squared error and the mean absolute deviation relationship. A drawback to using the mean absolute deviation is that the criteria is not differentiable. So if we want to minimize something like, if we set up this problem, min in some dummy variable b, 1 over n summation yi minus, and then we put in our prediction here, which is, I keep using b even though I'm trying to use a dummy variable, so let me just write this right, minus b naught plus b1 x1 plus so on and so forth. And here I'm being clear, these are absolute values on the outside, right? To set up this and minimize this in b, and I gotta have some subscripts on these i's, I'll just put a superscript, so keeping track of the observations in a superscript. When we minimize mean squared error, right, we have squared here, we can take a gradient of this expression, set it equal to 0, solve, that makes our life much easier. When we're working with the mean absolute deviation, this we have absolute values here, and so the absolute value function, of course, looks like this. Bring this down just a little bit there. And the result is that this is not differentiable, and so the optimization is more difficult, and by difficult here, numerically it's about the same, but we actually cannot take a derivative and set it equal to 0, solve for something in closed form. We have to use a numeric optimizer. I'll say the estimator, which minimizes mean absolute deviation, is called the least absolute deviation estimator, or the LAD estimator. I like LAD as a name for an estimator. It seems kind of human, but anyways. So that's mean absolute deviation. So here is the setup that I just wrote. Here I've written in vector notation with a row of a design matrix X and a vector B. I'll just say this is actually interesting. So I say that optimizing mean absolute deviation criteria is difficult, but not too difficult. The reason is that we can rewrite this mean absolute deviation estimator, the least absolute deviation estimator, as follows. So if I introduce these auxiliary variables t, I can rewrite this expression with the absolute values as minimize some expression in t, right, where I've replaced each of these terms by an inequality, or by two inequalities. So these t's are going to be the larger of yi minus xib and negative yi minus xib, right? So if we're minimizing this in t, well, of these two inequalities, we're going to choose whichever one is larger of these, right? And this actually ends up being, right, because the absolute value is either this or this, depending on which quantity is positive, right? This is actually the same as minimizing this expression here. So these t values are basically allowing us to rewrite these absolute values as linear inequalities, okay? And then, so what we have is a minimization problem. We have a linear objective subject to some linear constraints in t and b, and so this is actually a linear program with this rewrite. And so I hope you recognize this from your linear programming course, but it's a neat trick to rewrite absolute values as linear programs like this. So something maybe to just file in the back of your brain. The good news about writing this as a linear program is that we can solve it using linear programming tools, which are very well developed and a well-established technology. Okay, so that's the least absolute deviation estimator. Let's turn next to R squared. A benefit of using R squared is that it's unitless and between 0 and 1. Okay, so that means that I can bring you two different models from two completely different applications and say, okay, one has an R squared of 0.5, one has an R squared of 0.6, and you can directly compare those numbers. That's nice. That allows for better interpretation. Con is that it's similar. It's still similar to RMSE. Right, what's good? If you tell me an R squared of 0.5, am I happy with that? As R squared of 0.6, something I'm happy with. R squared of 0.25. Sort of the cutoffs are still still arbitrary, similar to RMSE, right? What makes a good model is still and very much an iterative process and trying many things to see what you can accomplish. Another con is that just from an interpretation perspective, R squared doesn't address what we intuitively think of model fit very well. And this is the reason that people have moved away from using R squared as a primary measure of model fit. And the reason is that actually R squared depends on the variance of x. So if this is counterintuitive, right? We don't think that variance of x should have an impact on our model fit, but actually it does. This is the variance of our predictor variables, right? The quality of the fit between x and y, we think it sort of depends on, right, what's the variance of this epsilon term, not what's the variance of x. But actually, if you make variance of x very small, you can increase R squared, and likewise, if you increase variance of x, R squared can be made arbitrarily small. And this is counterintuitive, and it's the reason why we have not used it as our primary measure of fit. We use root mean squared error. I say see truth about linear regression for more detail on this point if you have interest. I'm going to work just a numeric example illustrating this point in R, but for the theory talk of it, truth about linear regression has a nice discussion. So my opinion, R squared, like I said, more old school, used to be used more frequently as a measure of model fit. RMSE is a better measure of model fit, but it's important to know what R squared is so you can communicate with people who have taken statistics previously and might expect R squared to be presented as a measure of model fit. Also, if to interpret somebody else's results. If they present an R squared, you at least know what's going on. But generally, you should use RMSE. Okay, so let's demonstrate the LAD estimator in R. We're going to use the LAD function from the package L1 pack. Okay, so you should install it if you haven't there. Let me turn over to R. Okay, so here I'm picking up, this is, if you've taken a break between this lecture and the previous lecture, I'm picking up in working with the body fat data set. So remember in the first lecture I loaded up the body fat data set. This was percent body fat, and the interesting questions in this data set is, can we predict percent body fat using some other variables here, the age of the individual, the height of the individual, neck circumference, so on and so forth. So I'm picking up with this data set. We previously computed some confidence intervals and some prediction intervals. I'm going to load this L1 pack package so that I can compute the LAD estimator. So the LAD estimator is exactly like LM, except for instead of the LM function I use LAD. Okay. And let's just show what I have here. So here is hip and percent body fat. So I'm predicting percent body fat as a function of hip. And here I'm going to plot the LAD estimator in red. And then in blue, I'm going to plot the least squares estimator. So we see they're basically the same, right? We don't seem to have a big advantage in choosing one over the other. But let's perform a little experiment. So I mentioned that, if you have extreme values, that the LAD estimator will be more robust to extreme values than the least squares estimator. And so let's add a new row to the hip data frame, or to the body fat data frame. So I'm going to add this new row. I'm going to so I'm going to say that the percent body fat and hip values are 120 and 55. So do you see what I've done here is, this is a data entry error. So what I've done is I've said, okay, percent body fat hip, percent body fat is 120, hip is 55. So 120 is large hip, but I've plugged this value in for percent body fat. 120 for percent body fat doesn't make any sense, right? So I just have a data entry error where if I flip these, this would be fine. This would be what I would expect. A percent body fat of 55 would be high, but not completely unreasonable. Hip circumference of 55, or excuse me, hip circumference of 120 would be high, but not impossible, right? And so by switching them, I basically made them nonsensical, and I'm just replicating what would happen if I had a data entry error in this data frame. Okay, so I will plot the points again, and here we have my mistake and point thrown way off to the side, right? Well, what will happen to the two models? Okay, so here I'm going to build the LAD estimator and the least squares estimator. And I'm going to plot again, this is the LAD estimator, and this is the least squares estimator. So whereas they were more similar, right? The red is LAD, blue is least squares. They were much more similar, and by adding this one point, the blue and the least squares has been shifted. So as the LAD looks like it still fits most of the points very well, the LAD estimator has really has taken a hit, and its slope has changed to more dramatically than the LAD estimator to account for this mistakenly input point, right? So we can see, as I suggested in the slides, that the LAD estimator is more robust to extreme measurements than the least squares estimator. Also, I mentioned this, let's talk about R squared, okay? So what I'm going to do is I'm going to take, so set my seed for reproducibility. I'm going to make an X variable. This is just a quick simulation to illustrate some of my concerns with R squared. So here's an X variable generated uniformly between 0 and 500 samples, generates some random noise epsilon, Y, which is some linear combination of X and some intercept term, and Y2, which is similar except for we have a different slope here. So question, which of these two models has less error? Look at this, right? You look at this, I say, which one has less error? Well, the error term is exactly the same. It's actually the same random variable. I didn't even, the same sample. I took a sample of epsilon. I've added that same sample to both y1 and y2. So y1 and y2, they're both perfectly linear functions of x plus the exact same sample added to both of them. So they should be the same from our intuition's perspective. I'm adding a little bit of noise to this, the exact same amount of noise to both relationships x and y, right? But r squared does not capture this, whereas RMSE does. RMSE will capture the fact that these are similar, that these should be very similar in terms of model fit. R squared does not. So if I look at r squared, so here I have my multiple r squared, which is the one that's not been corrected for bias, 0.983 for the first one, whereas in the second one, my r squared is 0.69, right? Oh, these are the exact, right? These are the relationship x and y1, right? So this the same spread around the line. If I were going to draw a line, the same epsilon spread is around the line with slope 5 or the line with slope 1, right? And so, but what r squared is doing, as I mentioned, is it's penalizing this. There's a variance of x term here in the sense that here this has because this has a stronger slope. It's identified as a better fit, even though it's not a better fit. It just has a larger slope, right? The true model might not have. If this is the truth, this truth has slope 1. R squared is going to say, well, I really like this model with the larger coefficient, even if this is the right model, right? This is sort of the best you can do. The relationship between x and y is just noisy with some certain noise level. R squared does not accurately capture that. So again, I will reiterate, best practice, use root mean squared error. If somebody insists on speaking r squared with you, you know how to do it, but as I mentioned, it has some drawbacks and is less intuitive than root mean squared error. Okay, so let's conclude our alternative measures of model fit. So right, we have a lot of different ways to assess models. We can look at things like p-values to identify once we've diagnosed our modeling assumptions and figure out which ones are reasonable, we can use p-values. We've looked at mean absolute deviation, we've looked at r squared. These are all supplements to RMSE, which you can use as you attempt to find good models. My advice for how you choose between them, I start with RMSE. So when I'm fitting models, I just use RMSE, and then I reach for p-values, mean absolute deviation, or r squared for additional insight as necessary, but RMSE is my primary driver of model fit. An example of this is I might have two models which are very similar in RMSE, and I'm having a hard time choosing between them, right? If one of them has a lower mean absolute deviation, well, this is suggesting that maybe large errors are influencing my model, and if that's true, then I would just stick with the one which has lower mean absolute deviation. Okay, so this is sort of the philosophy is prefer root mean squared error, and if things are similar, then you can reach for additional insight, or for example, using mean absolute deviation and the least absolute deviation estimator. If you know that you have large errors just present in your model, maybe you just start with the LAD from the start, just saying, hey, we're going to use LAD because we know that we have large errors here, and it's just the environment that I'm working in. So that's another reason I might use mean absolute deviation instead of root mean squared error. Okay, so that's all I have in terms of alternative measures of model fit. So I hope y'all enjoyed this discussion, and I will see you next time.